First, let me write down the equation I would like to talk about. This equation is like this. So, especially we are interested in positive solution, of course, and also bounded energy solution. So here, epsilon is positive and the substance is small. This equation, rewriting this equation, we can write like this, because epsilon so there are many studies when epsilon is sufficiently large. Then it corresponds to the some semi-critical standing wave. There is the singular part of the program. So for this problem, when epsilon is sufficiently large, many people study this problem, including here the Yanyanmi denser and also Changsuri. So in this case, we have some localization. So the solution depends on the the shape or structure of this potential V. And here, I would like to talk about the other case, the other contrastive case. The epsilon is very small. So this is very large. So if we expect some little globalization, global effect of the V, so very constructive phenomena we expect, but there is some common the property for the two cases. So since the epsilon is sufficiently small, looking at this problem, this is very small, so we can see that this is a kind of some regular perturbation, you know. But if it is it just take a linearization, then we have a certain non-degeneracy, then we can see that it is some regular perturbation. But in general, it is not true. If epsilon goes to 0, then we have no continuation. So let me consider simply in the bound domain, U in omega. This is a bound domain, and we consider Dirichlet condition on bounding omega. So you may expect that if epsilon is sufficiently small, there is a solution very close to 0. But this is not the case. You know, from the viewpoint of some bifurcation theory or some implicit function theory, when epsilon is 0, it is not the non-degenerate. So we can apply some implicit function theorems. Or let me just we assume that the f u is a limit u is 0. Then so the u is 0 is a trivial solution of this problem. Near the 0, when epsilon is near the 0, there is only trivial solution. So there is no bifurcation. So we know that the epsilon is lambda 1. Epsilon is lambda 1. Lambda 1 is first eigenvalue of the minus alpha an operator with the Dirichlet boundary condition. Then this is U0 is bifurcation. In fact, we know further. In fact, epsilon is lambda k. Is k's eigenvalue of minus Laplace operator, and the u is 0. Is a bifurcation point of this problem. So bifurcation point means that when lambda is sufficiently close, bifurcation means that we have this kind of lambda here, epsilon, here u, and here is a lambda k. Here is lambda k here. Then here we have some trivial solution. So any neighborhood of this point has a solution close to this point, not on this line. At that time, we say there is a bifurcation point. So on the boundary domain, we know that rather completely which point is a bifurcation point. This is the only possible bifurcation point of this problem. Then it's natural to ask what happens when omega is whole entire space. Then there is no eigenvalue anymore. But in that case, we have a spectrum. The spectrum of Laplacian operator on whole space is continuous. So one can imagine that for any point, lambda, epsilon here, so there would be that point, epsilon 0 would be a bifurcation point. But that kind of phenomenon doesn't occur. Only for special epsilon, we can see that the bifurcation. This kind of result first obtained by Stewart. Stewart is the pioneer of this kind of problem on whole space, entire space. So, especially he considered the special type of some nonlinearity. Let me write down again the equation. He considers a rather slightly different problem. So this kind of problem, epsilon u minus g xu. Also limit x0 uniformly. Then especially typical type is gxu is the following. It need not to be radial symmetric. This is minus t u to the p. Like this. U. Then, so p, assume that p is greater than 1 and less than this exponent. Then we show that the 0. So 0 means that epsilon 0 and u 0. Now it's an infinity. U is infinity. It's a bifurcation. So we say there is a bifurcation from infinity. So for small epsilon, the solution, there is the solution. So whose norm goes to infinity as epsilon goes to 0. So in the boundary domain, for boundary domain, the bifurcation occurs 0. So it's the bifurcated from the trivial solution. But here, the bifurcation occurs from the infinity. So is a little different phenomena. So also bifurcation without any eigenvalue. So the bifurcation occurs at the boundary of this essential spectrum, not all spectrum, only boundary point. So in general, the bifurcation phenomena on the entire space is not easy to study completely. There are several kinds of aspects for the problem. So I can explain all the phenomena. Let me just explain some more result, some more study. For example, that many people all studied further Stewart and Cooper, Stewart, and also Benchi and Boltzmann. In some case, for different type of nonlinearity, for example, Benchi, Boltzmann proved that the bifurcation at any point in essential spectrum. So for different type of nonlinearity, and also this Cooper and Stewart studied the more general type of some equation when there is some coefficient here, for example, periodic boundary condition, or periodic function V, then we can consider Laplacian plus V like this. It's a periodic, for example, periodic function. Then we can observe that the more complex the singular spectrum, there is a essential spectrum, then they show that the bifurcation from the boundary point of a continuum of the sigma. So for certain V, the spectrum can be some interval and some isolated point like this, like that. Then if there is some interval in this spectrum, then at the boundary point, they could prove this some bifurcation phenomena.
Is it for all dimensions?
Yeah, basically all dimensions. This kind of phenomena does not depend on the dimension. So initially many people studied some OD problem, but that kind of approach also can be applied to high dimensional problem without modification. Okay. Some further study was carried out by Amusetti and Bariale, maybe from this time. They consider simply OD problem like this, epsilon V plus Hx with P. 0 in R. So also they were interested in positive solution and limit Vx is 0. So there is some difference here. So we have a parameter here in front of this one, and here only the parameter epsilon in the front of linear term. There is a slight difference. So in this case, we have some the bifurcation from infinity, but in this case, we observed some bifurcation from trivial solution. So, but there is a common feature that I will explain later. So for this problem, we transform ux by square root epsilon 1 over p minus 1 v x of square root epsilon. Then we have our equation hx over square root epsilon and we the p equals 0. So when epsilon is sufficiently large, I explained this, you can observe the localization, but here epsilon is sufficiently small, so we have some globalization. So we need something assumption for the h near the infinity. So we assume the limit x when x goes to infinity, hx converges to L, positive constant. Then, let's see what happens. So let x not be 0. Then if epsilon goes to 0, this goes to infinity. So this goes to L. So in exterior domain, this converges to L uniformly. So we have a limiting problem like this. It's L u to dp equals in R. So the Stewart approach was initial result of the Stewart was obtained by just a minimization argument, and motivated by his work, the Ambrosetti Bardiale adapted some Lyapunov symmetry reduction method, construct a solution for this problem. So since we have some good limiting problem, then they can apply the reduction method. So they proved that the following: if the integration -1 minus infinity to infinity hx minus L dx is not 0, then exists a solution of the problem. They did not mention the asymptotic behavior of this solution, but looking at their paper, we can see that the maximum point of this solution converges to 0. So a symmetric solution of this problem. Okay. So that solution bifurcating from 0. This bifurcate the solution from 0. So also in many cases for this kind of some part of the problem, we have this kind of some limiting problem. So my motivation for this kind of problem comes comes from the classical work of the Elliptic and Jaeyoung. They proved that they consider the more general type of some equation, the limiting equation in autonomous equation Rn, and of course it's positive, and the final solution. So they studied some more general type of nonlinear. Here, I just assumed the non-zero mass case. They also studied the zero mass case. In this case, they obtained the optimal condition for the nonlinearity, for the existence of the solution. So first condition is natural one, is ft over t, limit t goes to 0 is 0. Second is ft should be a subcategories a plus b t p is less than sublapse current. Third condition is index of t positive t such that the so we believe that this is these conditions are optimal condition for existence of this solution. So in fact, they proved that the existence of a least average solution on this condition, their result says that it exists a least energy solution which is radial symmetry. So this is necessary condition. So this is almost necessary and sufficient condition. So it's so natural to construct some solution for the part of the problem under these optimal condition. Here, they assume that just the F continuity. When we just assume that the continuity, we cannot apply some reduction method, since when they apply the reduction method, at least we need a C1 smoothness of the nonlinearity. So only hope is to use the variational method in this case. This solution is, in fact, multi-path solution. This is a multi-path solution. Multi-path solution. This is proved by Byeon and Tanaka. So, by multi-path theorem, it's not easy to prove the existence of some solution directly. But their proof is rather different with the multi-path lemma. They don't use a multi-path lemma, they use the direct minimization argument to prove this one. And later, they proved the structure, the level structure of the solution near the critical point. So they show that there is a multi-path structure. Then means that the solution is stable, and structurally stable. So since the multi-path solution is structurally stable, it should persist for some perturbation. So in the sense, we believe that there would be a solution for the part of the problem. So in terms of this one, and also this converts to A uniformly. So my expectation, my conjecture is this one. Without any condition like this, without any condition, then exists. Let me call this condition BL, BL2, BL3. So if BL1, 3 false, then exists a solution. Comes from the listing solution. But in fact, the ambiguity barrier is obtain the solution by weakening this condition a little. When this is 0 and some more condition, they could construct the solution. But that is not easy. In some cases, I could prove that. So before stating the result, let me introduce some result for the limiting problem further. So I said that the least any solution obtained by Elliptic is a radial symmetry, but this question is the symmetry of the any positive solution of this limiting problem of this one. So we know that the F, this is ellipse continuous, C01. Then by the moving frame method, we know this U is a radial symmetry up to translation. But F is just the C continuous, then we cannot apply this moving frame method, since that we cannot use the comparison principle for unbounded coefficient. Then we have some problem. Then just the one hope is to prove that there's some symmetry for the least any solution, since it is the most stable among all possible solutions. So when U is a least any is a symmetry, U is a least any solution. This was obtained by collaboration with Maris and Byeon Jaeyoung. So very recently, Maris developed a very nice argument to prove that the radial symmetry of some minimizer of the minimization problem. Then I realized that we could apply that kind of approach to this problem for the least any solution. And furthermore, we could prove in the paper, we could prove that the U is a radial symmetry and decreasing, non-increasing. But when we want to know that the exact fine asymptotic behavior of the solution, we need some strictly monotonicity. But here, using the certain type of the rearrangement or the polarization or any argument does not say any the strictly decreasing property of U. So we cannot apply such kind of technique. But so we could prove that the U is a strictly decreasing. UR radius is strictly decreasing. So It is obtained by collaboration with my student Young-Eri. It's surprising we obtain this kind of result using this POSTECH identity. Okay. So my object goal is to prove that the existence of solution without any condition for this kind of thing. But it's an ongoing project. It's not so easy. But now we could prove that when this integral is less than 0. And maybe that's nice thing. So if this integration is less than 0, then if it is a solution U epsilon such that U epsilon converges to a radial symmetry less than a solution of a limiting problem as equal to 0. Furthermore, maximum, you let x epsilon be the maximum point of U epsilon. Then limit should be 0. So there are two kinds of the problem here. First, the construction of this kind of solution and the characterization of this the behavior. So in the singularly portable problem, I developed a variational method to construct this kind of some solution in 2007 with Jaeyoung. We could construct a solution for the singularly portable problem, semi-classical standing wave. Then we applied that kind of approach to this problem. The strategy in the construction of the solution is to first consider the set of the approximating solution. In the Lyapunov-Schmidt reduction method, first they construct some solution manifold and they reduce the program to finding the critical point of the manifold. But in this case, we have no nonlinearity, since we have no even the C1 property of nonlinearity, and we just investigate some gradient flow near the solution manifold. Then in this case, non-manifold is a solution set. It's a compact, locally compact set. Then we investigate some gradient flow. Then we could prove that the existence of a solution with a certain energy level, lower than certain energy level. So in the sense we say it's the combination of the traditional variational method and some reduction method. And the applied the method to this problem. Then we have an existence of a solution U epsilon whose energy level, so energy is given by this one. We proved that the gamma epsilon U epsilon is less than this one. Something, the energy of the limiting problem's energy, plus here we have this kind of estimation. Here U 0 less V minus L. Plus it rho like that. So first we find a solution whose energy level is below than this one. The U is a solution of the limiting problem. This is a value at the 0. Then next thing, to get the asymptotic behavior of the solution, then we need a low estimation. Then we could obtain the low estimation, also this same type of some thing. Here U is the same, but here you can be different, so you should choose while the U, since there is the uniqueness, is X epsilon and V minus L dx. This kind of thing. So from this low estimation, we know that the X epsilon goes to 0. Since that we have some strict decreasing property of this solution U. So this kind of some and the approach, when we try to characterize the asymptotic behavior solution, this kind of the lowest estimation or upper estimation was this kind of some technique was used by the Wei-Ming for the Neumann problem. Also, we can see that the similar phenomena for this kind of a problem. Okay, I have just 3 minutes. Okay, let me stop here.